Okay, science time. Today we're talking about, well, let's just call it waves. Is the sound working? Yes, okay. Waves. Oh, kind of some bad kerning in between the W and the A, but whatever. Waves. What's a wave? Water. Is that the right answer? No, that's not to make, I'm trying to make Tiger feel bad. Surfers is her next guess. Is that, okay, let me think of it this way. Is that fundamental? Is that basic enough to be the definition of a wave? No. What is? Let's think of something that is fundamental enough that it can apply to all waves. Oh, Garrett. There is, okay, we could say there is some movement. Let's put movement up here. Let's put a question mark by it because we're not so sure about that one. What is true of a wave? Let's draw a wave. Surfers surf on them. So Tommy is fixated on waterways. Are waterways, let me ask you this question, are waterwaves the only kind of wave? No, let's list some other kinds of waves. Let's start with that. Okay, kinds of waves. Microwaves is a kind of wave. Microwave. I do not mean microwave oven. We're talking about a different thing. A microwave oven generates a type of electromagnetic wave called a microwave, which we'll talk more about later on. Miranda, what's another kind of wave? Radio wave. Tommy, say water wave. Water wave. I don't know what you mean by that. Oh, like the waves in a spring, in a Slinky toy. Other brands are available. A non-branded spring toy, yeah. Let's call it spring waves. Not the season, and not the little source of water in the ground, but the mechanical device. This kind of spring. That kind of spring. I'll put that in parentheses. What other kind of waves are there? Yeah, good. Sound waves. Okay. Let's put those kind of in their own separate little category over here. I'm going to put them in a different font too. Longitudinal. That's not how anyone ever has said it before, but that's how I said it so I can remember how to spell it. Waves. And transverse waves. Probably should have capitalized that too, since so it matches the other one I wrote. Transverse waves. These are types of waves, but they're different. Like, let's say it this way. These are different kinds of categories themselves. Like I might say that the types of dog are Chihuahua, Anatolian Shepherd, German Shepherd, Labrador Retriever, Golden Retriever. But there are also different kinds of dogs, where I could say smart dogs and dumb dogs. And that's not categories of dogs in the same way that this is, but it is still kinds of dogs. You see what I mean? So that's the same thing with these waves, that we have kind of now two different lists of different kinds of waves. Kinds squared of waves. There we go. So kinds, and we'll call these types. Even though those words mean the same, I'm just kind of arbitrarily using them to mean that these are not types of waves in the same way that these are, and these are not types of waves in the same way that these are. All dogs are either stupid or smart, aren't they? To some degree, right? There's a varying degree. Let's say it this way: all dogs, and this is not true, but we're going to use this as a attempt to get to the truth about waves. We can say all dogs are black or brown. Obviously, that's not true, but we're going to pretend like we're in a world where all dogs are black or brown. Can German Shepherds be black or brown in this world? Yes. Can Chihuahuas be black or brown? Yeah, they're different kinds of kinds. A better way, all dogs are either fixed or not fixed, aren't they? That is true. All dogs are either sterile or fertile. And so can an Anatolian Shepherd be sterile or fertile? Yes. So these are different kinds of kinds. So these are like kinds of waves of different types, and these are types of waves of different kinds. Shut up. Okay, but you know what I'm getting at. Do you know what I'm getting at? Because I don't know if I'm making myself very clear at all. let's put it this way. Each of these kinds of waves is one of these kinds. There we go. That's a little better. Let's draw these ones. Longitudinal waves and transverse waves. And then we'll try to, from there, we'll try to get a definition of waves. Longitudinal waves, do you need to go wait in the car, Tommy? Okay, longitudinal waves. I'm going to draw, what is this supposed to represent? Can you guess? A slinky. Other brands are available. But a longitudinal wave is when, which direction, if I have a slinky, which I do, and we're going to do a demonstration with this pretty quick, hopefully on the camera. If I have a slinky and you have a slinky, let's just undo it right now. I'll unspool the slinky of science. The other brands are available. This is not branded slinky even. The spring toy, the giant snake-like spring toy of science. Would someone grab that in so this doesn't get retangled up? Peyton, would you grab that in so it doesn't get retangled up? Peyton, would you be more comfortable doing this on camera or off camera? Would you be more comfortable being on the camera or not? Okay, well, you come over here somewhere, and if you happen to be on the camera, then I don't really care either. Okay, so here we have Peyton standing just off camera, yep. And you can't really see this at all. Yeah, you can if we lift it up high enough. Would you go over there? And there we go. Okay, so Peyton's just off camera, but she is over there. Keep it tight. And here I have spring toy of science. Yeah? You see it? Now this kind of wave, did you see it? It's not, pretend it doesn't wobble, but the compression here, look, see how this gets squished together? The camera can barely see that. See how this gets squished together? If I let go, then that little bit that is squished moves from me to Peyton. But when I say that little bit that is squished, is this part going pew and going all the way over to Peyton? No, let's put it this way, is the matter that makes up this spring toy, is this chunk of matter going to Peyton? No, it is not. So what is moving from here to Peyton? The energy. Okay, so keep holding that. The energy is moving this way. The energy is moving this way. What is a way that, let me phrase it this way. Would Peyton know, even if her eyes were closed, that energy is coming towards her? Yeah, because she could feel it. She can feel the movement. We use this word movement, ? She can feel the oscillation. Oscillation. O-S-C-I-L-L-A-T-I-O-N. Oscillation. What's that word mean? It's kind of like movement. It's back and forth movement. Something is, on average, staying in the same place, but it is moving back and forth. So when you are nervous and you're trying to give your speech in Miss Wedham's class and you're going like this, that's oscillation. You're not going anywhere, but you are moving. That's an oscillation. Okay? So that's what's happening here. Each little baby, each little thing, let's look at this one. Each little thing is moving back and forth, but it's not moving from here to here. This thing itself is not moving from here to here. The matter is moving just not from here to here. The matter doesn't go back all the way to the end. It moves back and forth. And that back and forth movement is called oscillation. Check it out. Let's make this really tight. Hopefully it doesn't hurt anyone. Hold on tight. Do you see this little red thing here? I think even the camera can kind of see this. Do you see the little red piece of tape here? Watch the red piece of tape as best you can. Did it go from me to Peyton? Did anything go from me to Peyton? No matter did, but did anything? Energy. She can feel it, right? You can feel it. But the matter did not go from me to Peyton. It's just going back and forth. What's that back and forth called? So which way is energy moving? When I do this, which way does energy move? Generally from me to her, which is the opposite of how I drew on here. So the energy is moving from here to here in my drawing, but the matter is just moving back and forth in an oscillation. Does that make sense? Okay, now let's look at this one. Let me loosen it up a little bit. What kind of wave was this? Do you remember from your reading? Wrong. This is a longitudinal. Great job picking the next one, though. This is a longitudinal wave. Because which way is the energy flowing in my diagram? That way. It's flowing, let's use a word. It's flowing right in my diagram. Which way is the matter? It's not flowing. Which way is the matter oscillating? On the which axis? Left and right axis. It's moving. So the energy and the matter are both going, we could say. They're both acting in the same axis. Energy and matter on same axis is the definition of a longitudinal wave. Now, we going to have this kind of wave. Oops, kind of stopped my drops there. Once again, we're still going to have the energy flowing in the rightward direction. It's really loud, but can you see what's happening? So now the energy is still moving. Let's stop it again. I'm going to try to do it a little bit. If I am doing this, the energy is still moving from me to Peyton, isn't it? Yeah, is it? Now each part though, where'd my red thing go?
I don't know.
It's all the way down by Peyton. There's the red thing. Watch the red thing. Now what's the red thing doing? Yeah, is it moving? Is the red thing going now from me to Peyton or Peyton to me? No. What's it doing? What do we call that? Oscillation. Except now the red thing, which my diagram is green. I've really done this poorly because I have the energy flowing the opposite direction. I have green instead of red and red instead of green. But the red thing in this is the green on this, and this is moving now up and down. So the matter is oscillating up and down. The energy is still moving to the right. What do we say about this? What kind of wave is this? This is a transverse wave. And this one, energy and matter are what mathematical function is between them? I wouldn't call it a function. What mathematical vocab word, I don't know what else to say, is true of the direction between them? They are?
Up and down.
Up and down is not a mathematical vocab word. These two things are?
X and Y.
Okay, they are what? What is the relationship between them mathematically?
Oh, parallel.
Try again because that's wrong. They are perpendicular. Are perpendicular. It's the opposite of what Lucas said. Just remember that. They are perpendicular. So this one is in the, but check this out. There are two kinds of perpendicular because we live in 3 dimensions. So right in the same direction, a longitudinal wave was this one. We could say back and forth. The energy is moving back and forth, and the matter is oscillating back and forth. This is a transverse wave in the y-axis, we could say. It doesn't really matter, but we could say that. This, here, stop it. This is a transverse wave in the z-axis. Does that make sense? So you can have, there are two different axes on which a transverse wave can occur. The energy is still flowing from me to Peyton, but now the matter is oscillating left and, well, to you guys, it's forward and backward. This one was up and down, which is still perpendicular. This one was forward and backwards to y'all. The energy is still left and right, and then the transverse wave was the matter is also oscillating left and right. Can it be both of these at once? Yeah, it can be up and down and left and right at once. And it can also be all 3 of them. It can be both kinds of waves. So these are the different categories of wave, types of wave, and then within them are different little baby kinds. So like, for instance, a microwave is electromagnetic radiation, and it is a transverse wave. In fact, it is a transverse wave both in the y-axis and the z-axis. It has an electrical component and a magnetic component. We'll talk about that in a second. And a water wave is really, in a lot of ways, it's all 3 kinds. There's a circular motion to it that is both longitudinal, it's moving in the same direction as energy, and it's transverse, moving up and down relative to the energy. Okay, thank you. Thank you, Peyton. Would you, Sage or Peyton, would you roll this back up very neatly without getting it tangled? Would you guys give Peyton a round of applause, please? Okay, very good. That's something we can't do with the freshmen because they get really out of hand about rounds of applause. So let's define a wave. What is true of all of these waves? They all involve what? Oscillation. Okay, so all waves involve a repetitive oscillation and the flow of energy. So is it movement? Well, so there is movement. The energy is moving from place to place, but the matter itself does not move. A wave transfers A wave transfers, fill in the blank. A wave transfers energy. It does not transfer matter. Matter can ride along with the wave, but check it out. Tommy loves surfing. Tommy will not stop talking about surfing. Every single word that fall out of Tommy's mouth is about surfing. But check it out. This is the ocean. This is a beautiful ocean, if I do say so myself. And you are a surfer, and this is an ocean, and you spawn into existence on the ocean, on your surfboard. You were first born. You think to yourself, where am I? Why am I here? Am I a surfer? But you are just on the ocean. You have no prior movement, is what I'm saying. You've just instantly become on the ocean. How are you going to behave?
You're just going to sit there.
You're going to oscillate. And because it's a water wave, you're actually going to be oscillating in a circular pattern. You're going to be going both up and down, and in this diagram, left and right, which ends up being a circle. That's how ocean waves work. But you're not going to have any net movement. You're not going to be moving from here to here. So then how do the surfer, in real life, because we know surfers do move, how does this surfer that wasn't spawned into creation right at this second, how is he moving from here to here? Well, he has the same momentum that he started with. So he was paddling before, and that whatever speed he was paddling at is the speed at which he continues to do that. He's still going to be riding the wave, which is what the surfer loves to do if I know anything about surfing. Still riding the wave, just like this guy, but he also has his own movement. Has anyone in here ever swam in a place where there is waves? Raise your hand, please. Wave pool counts, yeah. You know that if you are just kind of loafing in the wave pool, you do just go up and down, or maybe up and down in a little circular path. How do you move? Well, you have to have swum. You have to have applied your own energy, because matter is not carried by a wave. How then, okay, now it's a pirate.
Jack Sparrow.
It's Jack Sparrow. He has dreads, and he loves his hat, so he has a little hat, and he has a beard.
His jar of dirt.
And he's going to throw his jar of dirt into the ocean. Throw! But then the jar of dirt it does the wave thing, but it keeps on moving this way. Why is that? The wave must carry matter. I've proven Mr. Keim wrong.
Because he threw it.
Yeah, because he threw it. It just has the same motion it had when it began, and the wave is still moving up and down, but now it's being carried by the wave. So what if it wasn't Jack Sparrow who threw it? What if it's you who doesn't surf and who isn't a pirate walking on the beach, and you see a message in a bottle float up to you? You're watching. No, that's not what I'm asking you. You're watching the message in the bottle come to you. Surely Mr. Keim must be wrong. The waves actually do carry message in a bottle. No, what is happening? There's other things going on here. Maybe. Probably not.
God sent it to you.
Maybe. Doesn't really matter whether that's true or not, though, for this. Okay, yeah, either wind was giving it some force or the oceanic currents were giving it some force. But anytime something is moving from place to place on a wave, there must be some other force acting on it. Because the wave only oscillates. It only oscillates. Everything else being the same, the wave only oscillates. What is transferred by a wave? Energy. How does matter behave in a wave? No, it doesn't. It oscillates. Okay, last thing, and then we're going to be done with this. Let's draw a diagram of our two kinds of waves again. Let's draw a diagram of our two kinds of waves again, and we're going to label the anatomy of a wave. What's anatomy mean? Yeah, it's the parts of something. When you're talking about human anatomy, we were talking about the sternum and the fingernails and all that stuff, the parts of the human body. And we're talking about the anatomy of a wave, we're talking about the parts of a wave. So here I have, what kind of wave is this?
It's a transverse.
Transverse. And here's the usual way that we depict a longitudinal wave.
With dots.
Usually. Actually, usually when they're expressed, we just use a transverse wave to show them. But what do these dots represent? The close together dots represent when I had the slinky squished, not a word, and the far apart dots represent the parts where it wasn't squished, right? And it's a repeating pattern, just like this one was. This one is a repeating pattern of up and down. This one is a repeating pattern of squished and not squished. Yeah?
Yep.
Compressions, we call them. These ones are compressions. What's compression mean? squished. And rarefactions. Rarefactions. For something to be rarefied means there's not very much of it. A phrase that you will never have heard because you're not sophisticated is if you say something was in rarefied air, that means it's pretty unusual or really sophisticated and unusual. Like, we might say that Tommy, as world champion 11-year-old team roper, I don't know what you do with your life, but some rodeo crap I don't know anything about, is in rarefied air, meaning that not very many people can do that. Rarefied just means it's not very common. So the dots in here are less common. They're less pushed together. So let me draw a little line here because I'm kind of messing into my other drawing. In the longitudinal wave, it's made up of a repeating series of compressions and rarefactions. And in the transverse wave, it's a repeating series of, what's the low point called? Does anyone know?
Oh, I remember reading it.
Trough is how the word is pronounced. And the high point is called a crest. In the transverse wave, this rest point is, I think does your book call it a rest point? This kind of average line, if we average all the crests and troughs, we get this what's sometimes called a rest point or a baseline. Like in a heartbeat. Yep. It's a little bit hard to draw, but in the transverse wave, in the longitudinal wave, the baseline is the average way they are when they're not compressed or rarefied. So it would be something between squished together like this and spread apart like this. It's some amount of distance between them where it's not either of those things is the baseline, but it's kind of hard to draw that. Both of them have a, what have I drawn here you should know from your reading? What is the distance from one thing to the same thing on the next wave? What is this called? The distance from one point on a wave to the same of the, this should probably actually be drawn to here, yeah. What is it called? Wavelength. The wavelength, which is measured usually in meters or some version of meters. And then we have the, what's this called? The distance from the baseline to the highest crest, or the baseline to the lowest trough? No. Amplitude. And it's hard to draw this in this too, but in amplitude in a longitudinal wave is how compressed the compressions are and how rarefied the rarefactions are. Actually, have you ever seen an explosion YouTube video where you can see the shock wave? In very, very high amplitude longitudinal waves, there's a vacuum in here. There's no matter at all. The matter is all compressed into compressions, and there's nothing in between them. And that would be like an explosion. That's one of the loudest sounds. Amplitude for a transverse wave, longitudinal wave, of which sound is a kind. Sound is a kind of longitudinal wave. When I talk, can you hear me talking? When I talk, what's happening is my vocal cords, which are down here, are going, and they are smooshing together air that's coming out of my trachea, and they're spreading apart. And that's making sound waves. They're squishing together air and spreading apart air. And the air that's inside of me is not coming to your ears. That would be disgusting. The air that's inside of me is not actually moving because a wave doesn't do that. But these air molecules that are down here bump into these air molecules, bump into these air molecules, and eventually the air molecules get bumped into each other and they go into your eardrum, which then goes and it sounds just like what I did. But the louder I make my voice, the more squished together the air gets, and that means that the more spread apart the rarefactions get. Squishing together. Amplitude is sound volume for sound waves. Well, we'll talk more about those specifically in the future, but you have questions about the basic properties of a wave. Do you?
I don't think so.
Okay. Bye.